Probability Structure Analysis by Geoff Farthing.
The purpose of my study is to discover more detailed stemmata of New Testament texts, using Mark in Family 13 as a particular example.
In 1941, Kersop and Silver Lake give this stemma for Family 13 in Mark, but they specifically say that while the stemma is basically correct for the text of the manuscripts shown, it does not show corruption from other texts, particularly the Byzantine.
The Lakes have formed their stemma using a small number of carefully selected variations, which are likely to show the underlying stemma. My approach is to count nearly all of the variations. By increasing the amount of data used, I hope to show much more of the fine detail of the relationships. The lines, branches, or stems, as I call them, of the Lake's stemma each relate to a specific text combination.
For instance, the stem D to E creates the combination 13-3-4-6 against the rest.
The Lake's stemma shows 15 real text combinations, 10 where one text stands alone, and 5 where several texts stand against the rest. Sadly, of course, full data for 1689 is no longer available, so we can only consider 9 texts here. But for 9 real texts, there are over 250 possible combinations. In my data, over 100 are actually found in Mark for these 9 texts. In probability structure analysis, I am seeking to investigate, account for, and represent the more elusive complications alluded to by the Lakes, and to use data from most of the text combinations rather than a select few. Probability structure analysis does not work with the frequencies of the real text combinations directly, but seeks to create a model whose text combinations parallel the real combinations as closely as possible. A good match suggests that the probability structure model is a good enough representation of the underlying stemma of the real manuscripts. The model has these very simple assumptions.
1. That all the texts consist of a finite number of possible points of variation. 2. That each possible point of variation can have only 2 forms. And 3. That each copying process is characterized by a specific probability that each possible point of variation will change. I hope a very simplified example will help. Consider a text represented symbolically by 26 possible points of variation, each identified by a lowercase letter. Each possible point of variation also has one other form, identified by an uppercase letter. We take a manuscript A with this text, where every possible point of variation is in the lowercase form. B is a copy of A, made with a 40% chance of each point of variation changing. This produces 10 changes. The second copy C is then made with 30% chance of each point of variation changing. This produces 8 changes. The crucial and fundamental thing to notice is that the changes forming B and those forming C coincide 3 times by chance at D and N and U. The result is that B and C share changes by chance, despite sharing no copying history.
With probability structure analysis, however many or few copyings are represented, every possible text combination will be assigned a frequency, though in some cases, of course, figures may be insignificant. The strength of probability structure analysis is its ability to give frequencies to the combinations formed by chance duplications and chance reversals of changes, which so bedevil all attempts at the understanding of real texts. The further issue that probability structure analysis can deal with is the case where a text has more than one parent. This can arise in various ways. A scribe may find that some part of his copy text is missing. A number of manuscripts of Family 13 in Mark have missing sections. The scribe may then find a second copy to complete the work. Or a scribe who virtually knows the text by heart may partly correct the text of the copy as it's made. These circumstances can be called mixture, conflation, or contamination. Probability structure analysis calculates these by proportioning two or more stems that feed the conflate text. Clarifying the data can be complex, but the presentation is quite straightforward.
C is partly derived from A and partly from B. The dotted stems are given proportions, which must add up to exactly 1, of course. The full stem is given a probability which converts to a mean number of changes. The assumed text X is a convenient fiction to assist calculation.
But can so simple a system usefully model the relationships of actual real texts? I have collated data on the 9 texts of family 13 in Mark, using the wonderful database at Munster, for which I am hugely grateful. My analysis is based on about 2/3 of Mark. Some texts have small gaps, but the largest omission from my data is for 124. While the whole text is on the Munster database, the section 939 to 1334 is not yet transliterated, and I've not had the energy to do this for myself.
The best simple stemma, that is a stemma lacking any conflate texts, for family 13 in Mark is this. This stemma is produced simply on the basis of the numbers with no human intervention, which shows that the mathematics do produce a credible model of the relationships of these texts. But it does differ from Lake's stemma. 4 differences are obvious. 1689 is sadly missing, and text 69 is moved. Text 543 is also moved, changing places with 826, and 828 has moved. But probability structure analysis results offer more information. It offers probable numbers of changes on each stem. Looking at this information, I would suggest that while 69, 543 and 828 have moved in comparison to Lake's stemma, they have not in fact moved very far. Now this is the best simple stemma from this data, but has a trivial probability, suggesting it fails to take into account one, or more likely several, conflate texts. With very limited time, I must simply present what I believe at present to be the best analysis. The chi-squared error figure for this stemma is 37.35. By making 69 conflate from B and C, error is reduced by 4.3 to 33.05. By adding a conflate text H, separating 13, 346 and 828, this figure is reduced by 10.18 to 22.87. By adding text from 124 into 346, the error reduces by 4.78 to 18.09 and a just acceptable probability of 3.4%. By adding text from 124 into 983, the probability becomes 5.39%. By adding text from 983 into 346, the probability rises to 11.5%. By adding a stem E to K to group 346 and 828 more closely, the probability is 18.6%. And by adding text again from 124 to 828, the error becomes 4.07 and the probability 53.96%. These results probably raise endless questions in your minds. It certainly does in mine. For instance, why is the text of 124 so prominent as a contaminant? I suspect it is because 124 carries more Byzantine text than any other, and the links are the computer's attempt to indicate Byzantine contamination in a number of texts. I then wondered if these links would be better situated between 124 and the node B. The computer agrees that they would, giving a final probability of nearly 70%. I suspect this point in the stemma indicates the point of earliest text based on the information in this data. I am investigating further. However, my purpose here is not to give any final answers, but to demonstrate that this form of analysis shows promise of a much more exact and richer understanding of the relationships between the texts of the New Testament, at least in small groups. A further advantage of probability structure analysis is that within certain probabilities, the changes in the text on any particular stem or in any conflation can be identified. Please watch this space. Thank you for listening.